Okay, welcome everybody. We are into the point where we're doing some homework problems, and I'm wondering how you guys were doing on the homework problems. You doing okay? Okay, let me share my screen here, and let's see how we did on these. I think that the first problem was pretty straightforward. This is what is due today. Evaluate the optimal 20 questions for p is equal to a third, a third, a third. And I think that that one's actually pretty easily done. Do you agree with that? Okay. You just about lost your hat there. So what about this p is equal to an eighth, 3/8, a tenth, 2/10, and well, the one that's done here. Now, if you got this right, then the expected number of questions should be between the entropy and the entropy plus 1. Did anybody get that result? Okay, wow, that's very good. Okay, well let me choose what to do. Unfortunately, I'm at a place where I have no this is not a fair coin. I'm flipping a little pill pod. And you guys are probably too young to know what a pill pod is, but that's where older people put the pills that they have to eat for the day. So since you've forgotten your numbers, we'll go with let's see, Theo as 0, Glauco is 1, Matthew is 2, Adam is 3, and Justin is 4. So let me do this, and we got 0, 1. Okay, so Glauco, can you show what you got here? And I will quit sharing my screen and allow you to share your screen. And let's go for it. What'd you get?
Okay, I get the 20 questions for the second problem.
For the second problem, yes.
Okay, so the entropy is 2.167. And then after a couple of trials, I got the optimization for this path of questions, starting by is less than 3, yes, no, and then less than 4. And so I got the expected number of questions. I got 2.225. So it's between the entropy and the entropy plus 1.
Okay, and what probabilities did you apply for each of the numbers? Did you have 1 was 3/8, 2 was 1/5, etc.?
Yes, I ordered the probabilities from larger to smaller.
Okay, the largest. So 1 is the largest. So 1 would be the 3/8, and the smallest would be a tenth, I guess, or something like that, right?
Yes.
Okay. Okay, and so this worked out. So you asked if it was greater, and that's important to do. I don't know if you can work it any other way. You might be able to, but
I worked it in a couple of other ways, and still the expected number of questions was between the entropy and the entropy plus 1. But this is the smaller number I got.
Okay. Oh, is that right? So there were some that were less on the average, but still between the entropy and the entropy plus 1.
They were more questions in average, but still in between the entropy and the entropy plus 1. Yes.
Okay, but the number of expected value of questions you got was what?
In one case, it was 2.275. In another case, it was 2.25.
Okay.
So this is a little bit smaller.
Okay. Okay, great. Anybody get anybody else want to comment on this problem at all?
Well, okay. I did do it a different way, but Glauco's right. I realize now mine's non-optimal. I got an expected number of questions of 2.3.
Okay, and what was your approach? Was Glauco kind of tried to trial and error? Did you also have to arrange your probabilities in ascending order?
So I didn't really put mine in an order like that. I just kind of left them as the probabilities, and I had like the 3/8 and the 1/8 as one half and the tenths all in the other half. But my problem is I gave the 1/8. I got to the 1/8 in 2 questions instead of 3 questions,
Okay.
meaning one of the 2/10 was at 3 questions, which is a higher expected number of questions.
Okay. So interestingly, if you take the course on information theory, you will find out something called Huffman coding, which is an algorithm that allows you to get the solution to this problem exactly. It's beyond the scope of what we want to do here, but there is an algorithm for getting these results and getting them exactly, which is really kind of cool.
I have
And,
it.
yeah, Theo.
So on this problem, we were able to organize, like we sorted our probabilities in, I think, descending or ascending order.
Yes.
If you have data that is ordered already, would you just create some arbitrary like number scale and then put your different groups of data on that?
No, you would have to. The Huffman coding, if I recall, requires you to order your probabilities from smallest to biggest, and then is an algorithm on how you combine your probabilities for your tree.
Okay.
Now, the thing we didn't go through, Glauco, is the expected value of 2 to the minus L. Was that the same result? So yes, all of, okay, so you have your summation of all of your paths here, and it added up to 1. And what was the expected value of 2 to the minus lambda k? That was probably the same result, wasn't it? Or did you do that? Glauco, you're muted.
Sorry, I was speaking for a long time. I did this at the bottom, and I added all the probabilities, and I got to 1.
Okay, but I think I asked you all to do the expected value of 2 to the lambda.
The expected value of 2 to the lambda. Okay, I
Yeah, in other words,
done that.
okay,
I haven't done that.
it'd be k times 2 to the minus. Did anybody do that?
I didn't. I did the same thing Glauco did, just showing that they summed to 1.
Okay, to complete the problem, you need to you'll need to do that. Okay.
I did it, and it was the same as the expected number of questions. But
yeah, it should be the same as the expected number of questions. But it's interesting that you can talk about the relationship to the expected number of questions to the path length to get to the questions. I don't think that that's intuitively obvious until you play around with it a lot. So please include that. Okay, with that, let's go back to the spreadsheet, and one of the popover from last time was from chapter 3, problem number 13. And 313 is a very interesting problem because 313, which I have here, uses something called Euler's Basal Problem, I believe. Let x be a random number with a probability mass function, p sub k. So this is the probability mass function for k is equal to 1, 2, etc. Estimate the value of c numerically. Did anybody do that? And what? Okay, well, let's do the flipping here. That doesn't work very well. Okay, well, we got 0, 0. Theo, you're up.
Yes, I am. Looks like I did a different one, and that's my bad. I think last night I read the number wrong in the textbook.
Okay, that's okay.
I'll correct
Let's
it.
Let's go ahead and do that. Okay, 1, 1, which is 3, 0, 1, 3. I guess that's you, Adam.
Yep. All right. Let's see. I think you have to stop sharing so I can share.
You're right. It's amazing how good we're getting at this of navigating the Zoom thing. Okay.
Yeah. All right. So white.
Oh, you looked it up, didn't you?
I looked it up. I used a Goodfin Wolfram alpha
Okay.
and found that the series goes to c pi squared over 6. And we also know we want it to sum to 1. So then c must equal 6 over pi squared, which is approximately 0.6.
Okay, this is interesting because the thing you have bracketed, I believe it was the ancient Greeks or some civilization used to think that pi was the square root of 3, or no, square root of 10. No, square root of something. Pi is equal to 3.14159. Oh yeah, about square root of 10. They used to think it was the square root of 10. And you notice here with this approximation, if pi was the square root of 10, then pi squared would have been 10, right?
Mm-hmm.
And it would be 6 over 10, which is 0.6. Of course, pi squared is not equal to the square root of 10, but it was an interesting conjecture early on. So it's a good ballpoint idea. Okay, yeah, this is, so did you do this numerically?
I asked Wolfram alpha what the summation was.
Okay, well, our textbook is probably dated, probably recognizing that didn't work. Okay, well, that's acceptable. I mean, you did a modern solution. Okay, the probability that, let's go to B now.
Right, so the probability that x is greater than 4 is the same as 1 minus the probability that it was 1, 2, or 3. So I calculated the probabilities for 1, 2, and 3, subtracted them for 1, and got
Yep.
0.173.
There we go. Okay, and then the next one I think is just as straightforward, right?
Yep, between 6 and 8, add 6, 7, and 8.
Right.
So
Now,
I have a question on B. If you're finding the probability that it's greater than 4, wouldn't you have to also subtract out 4 because you're not wanting to look at 4?
He's
yes.
right. He's right.
Yep.
Okay. Yeah, that little equality sign underneath the greater than threw us off. So yeah, if Adam had included the plus P4, he would have been right. What was the answer that people got when they used the P4?
I got 0.1345.
Okay, 1345. Okay, so that was that. Now, you know, I remember going over the Basal problem. I'm not sure if it was in here where Euler evaluated that infinite sum. Did I talk about the Basal problem in here? I don't see any responses. Well, this was Euler's big deal. This was his claim to fame. And it even has an entry in Wikipedia. And the Basal problem was summing up the reciprocal of the sum of the square, or the reciprocal of the squares of all the integers. Now, if you're familiar with infinite series, you know that just if this was 1 over n without the 2 here, that's a divergent series and that goes to infinity. But this was a problem
Dr.
which,
Marks?
yes. Oh, I'm not sharing the screen.
Mhm.
Okay, and I thought I was being so clever. Okay, well, first of all, before I show this, I want you to notice that this problem says you have to sum up the 1 over k squared. Do you see that? So you have to sum that from k is equal to 1 to infinity. And this was historically something called the Basal problem, and was Euler's first big was his first big great paper. And the Basal problem asked for the precise value of this summation. And if you evaluate it numerically, according to Wikipedia, you get this 1.644. But Euler found the exact formula to be, as Adam showed in his solution, pi squared over 6. And this was first worked out in 1735. So right now we have it at Wolfram alpha. So we've come a long way since 1735. when he showed that it was equal to pi squared over 6. So that's a little historical comment. I always like to look at historical perspectives. And Euler was possibly the greatest mathematician that ever lived. He was just astonishing in things he did. Let me show you here, for example. Let's see. This is a page in Wikipedia that shows all of the things named after Euler. Euler was incredible. He lost the sight in one of his eyes. You can see his eye kind of withered here. He was in St. Petersburg. But these are the things which are named after Euler, okay? He has conjectures, equations. In fact, the E in e to the x is sometimes called Euler's number. Some people say that the E and the e to the x was named after Euler. It wasn't historically, but it could have been, since E is Euler's number. And you can see equations, ordinary differential equations, partial differential equations. He has a bunch of stuff named after him. Formula, Euler's formula. You're familiar with this. I think that everybody that's had complex variables is familiar with e to the jx is equal to cosine x plus j sine x. Polyhedral formula. Man, I wish I had time to go in this. This was really interesting. It's applicable to any polygon that you write out. And so it goes on and on. Numbers, Euler's number, there it is. E is equal to 2.7. It's the base of the natural logarithms, theorems, laws, other things, topics, derivatives, integrals, and logarithms, geometry and spatial arrangements, graph theory, music. I have to look up the music. I didn't know about that. Number theory, physical systems, polynomials, and a bunch of other stuff. So the guy was really prolific. I mean, he did incredible stuff, and was, again, maybe the greatest mathematician that ever lived. So that relates to the homework problem that we have. Okay, let's, I think, was that it in terms of the problems that we looked at? Let me put this back up. I forgot what the homework was.
I think that was it.
Okay, that was it. Okay, so very good. Thank you very much. You guys did a good job. Yeah, see if you can do this. The expected value of 2 to the length, and it's going to be exactly the same as the expected number of questions. Okay, for next time, we have covered transformations on a random variable. So I would like you to show, one of the things we purported was that if we had g of x, that was the nonlinearity that we had in the transformation. If we had a g to the x, and that was equal to the distribution, and it would transform a continuous random variable to a uniform random variable, is what we said. And one of the things I want you to do, which we didn't do, is look at what if x is a discrete random variable? What happens to this transformation into a uniform random variable? And it's not pretty. I will tell you that it isn't pretty. And then a Poisson random variable. I think it's very interesting because it packs the probability mass functions really close to each other. And so this is the synthesis problem in making a arbitrary random variable into a uniform random variable. And then the converse is that if you have a uniform random variable and you want to transform it to another random variable, what g of x do you use? And I would like you to prove that. I gave you the results in the lecture. I gave you the results in the lecture, but I would like you to prove it. Okay. And then some specific applications. Find the distribution when x is uniform on minus pi over 2 to pi over 2. And the nonlinearity is g is equal to the tangent of x. What you'll find out is that this is the Cauchy random variable. And that's kind of cool. I'll elaborate on that in just a second. Find f of x if x is 0, mean, and y is equal to x squared. This is another one. You know what? I might change this. Yeah, I think I'm going to change this. I'm going to change this to the magnitude of x. Whoops, where'd it go? Okay, it doesn't want to do what I tell it to do. Now, why might we want to do this? Many times, if you look at, for example, at the velocity of an air particle in a room, the velocity in the x, y, and z direction, all three components are Gaussian. So it's a random variable. So if we have a particle, which is in an ideal gas in the room, it's going to be vibrating. It's going to have a velocity, which is a Gaussian random variable. This was proved in the Maxwell-Boltzmann distribution, as if I recall. Now, you might ask for the velocity because the velocity is Gaussian. But what if you wanted to know the distribution not for the velocity, but the speed? And the speed, of course, is equal to the magnitude of the velocity. In one dimension it is. So this is a simplified version of this more general information. And so if we have a Gaussian velocity and we want to transform it to the speed by taking the absolute value, not caring about the direction, this would be the transformation that you would use. And you'll find out it's one of the familiar random variables that I gave you when we listed a bunch of random variables. And then I want you to find g of x, transform a centered Cauchy to a uniform random variable. That's one of the special synthesis questions that we had, and this will be due a week from today. So next Tuesday, please look at that. And if you have any questions, we'll go over them and talk about them then. Any questions at all? Okay, well, I'm doing very well because I am explaining things excellently. Because there's no questions, right? So this is kind of where we stopped last time, is generating random variables. And this is the synthesis and synthesizing random variables if we want to take something and make it a uniform, or if we want to take a uniform and make it into an arbitrary distribution, then we use these results. We also showed that the transformation was not unique. So we're talking about transformations on random variables and functions of random variables. One of the most important that we have is the idea of an expected value. Many times people look at expected values and don't really talk about what expected values mean. Okay, can you still hear me okay? Okay, I unplugged my headset instead of what I wanted to unplug. So I need to plug this in. This is my handy dandy overhead. Where does it plug in? Okay, it doesn't look like it plugs in this side. I don't know. They don't put enough USB ports on here. There we go. Okay, there we go. Let me elaborate on this a little bit. The expected value of g of x. This is important statistically, and I wanted to go over exactly what this means in some sort of sense. Suppose that we had. Okay, do I have? Yeah, I do. Okay. Suppose that we had a bunch of random variables here. Where'd I go? Oh, we're up there. Okay, you know what? I can't track my cursor here. Okay, but we have an x. And so we gather data. We gather data such as, let me just use integers here. 1, 3, 2, 1, 4. And so this is just random data, random numbers that we generate. And these are samples from a distribution called f sub x. So these are random variables which are chosen in accordance to f sub x. And of course, what we do is we many times take the average, right? So here we have 1, 2, 3, 4, 5, 6. So I don't want to, yeah, let's go ahead and add those up. This would be 4, 5, 6, 7, 11, 13. So this would be 13 over 6, right? That's the average of these numbers. Now, this number should be close to the mean, and that's the reason we use averages. And we'll literally prove this later on, that the average approaches the mean. And if you have a longer list of numbers, the closer this average will be to the mean. Say on the other hand, now we have another column, and this column, so this, I should mention that this is, will approach the expected value of x. It will approach the expected value of the random variable. But what if we have something like x to the 5th? Let's see, can I go that fast? No, I can't. Let's do x cubed. X cubed would be 1, it'll be 27, 8, 1, 64, and 8, okay? So that would be x cubed. I would add those up. And I would divide by n, and that would be an approximation of the expected value of x cubed. I can do weird stuff. I can do e to the x. So I can go down and I can add these up and take each one of these to the eth power. I could add them up. Sorry, I'm going into that tutu. And I could add up all of these e to the x's, and that would be approximately equal to the expected value of e to the x. Okay, so each one of these is the expected value of any of these things can be generated empirically if you have enough data. You simply take the data and perform the function on it. You do the average of it, and the average will be pretty close to whatever the expected value is. So that's our interpretation of the expected value of x sub n. Does that make sense? One of the most commonly used moments is the expected value of x to the n, which is referred to as the nth moment, as you can see here, the nth moment. And the first one is the mean. Now, if you've taken a course in statics, and I don't know if they even require that anymore. It turns out that if you have a piece of wood that is cut out like this, so that's a piece of wood, okay? Trying to give it a third dimension. That wasn't very good. But you cut out a piece of wood and you ask yourself, where does that piece of wood balance? So I'm going to try to draw a hand here, which is balancing that piece of wood. And you put your finger on that balancing point. That is the mean. That is the first moment of the piece of wood under the assumption that the piece of wood has a unit area, which our density function does. So you always interpret the mean as the point where the probability density function balances. Now, this is much different than from a case where if you have 50% on one side and 50% on the other side, that point is called the mode. No, it isn't. It's called the median. And I think many times there is a confusion between the median and the mode, but the median is where the density function balances. The mode is where there's 50% on both sides. And so they are different. And sometimes they are equivalent. If you have a nice symmetric, like a Gaussian random variable, then the mean is equal to the mode. But if you just look at a single side exponential, the mean and the mode are, I'm sorry, the mean and the median, I keep saying mode, I mean median. The mean and the median are not the same. And that's something which is easy to show. So the mean is not equal to the 50% dividing line. And you hear, in fact, I had this conversation with my son about a week ago. He says, well, half of the, if you take the average person, half of them have an IQ less than average. No, that's not true. The average, like the mean, does not divide the density function into two equal parts. You cannot say that half of them are worse than the average. You can say that half of them are worse than the median, but not half are worse than the average. So this is really good. And of course, the other result is this the idea of the second moment, and the second moment especially is used for the variance. Now, once you have a description of a probability density function, and you go to your boss and you say, you know what, here's the density function. This is my f sub x of x. And your boss says, hey, that's too much information. I want you to simplify the explanation. So you can say that it has a mean and a standard deviation, which of course is the square root of the variance of x. The variance measures dispersion. You can see down here that this variance is a measure of dispersion. That measures how far the density function is spread out. It's not the only measure of dispersion. Can you think of another measure of dispersion? One of them might be the range of the random variable. You know, what's its minimum value, your maximum value minus your minimum value. The range, that tells you how much it's spread out. Then there is this x bar up here, which is a measure of central tendency. And the central tendency kind of tells you where the density function is centered. And one of those measures is the mean. But we also have things like the median. That's also a different measure of central tendency. And the mode, which is where you get the maximum value. So all of those are different measures of central tendency. The most commonly used, however, is the mean as a measure of the central tendency, and sigma, which is the measure of central tendency. Sigma, of course, is the standard deviation, the square root of the sum of the squares. Yeah, Theo?
If you have a probability distribution that is asymmetric around the mean,
yes.
Is there ever a way that you would have some, like say like a standard deviation going in one direction and a standard deviation going in the other direction, just so that you could say that the spread going down from the mean, say, is larger than the spread going up from the mean?
The way that we have defined it, the standard deviation is a single number. So if you had a weird, density function, for example, I'm running out of space here. Say you had a density function which looked like this, a little bit of probability mass there. How fortuitous, I got rid of everything. And you get a little bump here. So you have two bumps in your probability density function. You still have a single standard deviation. You still
Okay.
have you still have just a single spread. Now, this is important. Suppose that the random variable, suppose we're in the lab and we're measuring the random variable, and it turns out that X, this value that you're measuring, has units of volts. What is the measure of the variance? The unit of the variance is going to have units of square volts, isn't it? So the reason that we use the standard deviation is because the standard deviation has the unit of the same thing you're measuring. So sigma has, in this case, units of volts. How many volts in terms of the dispersion are we talking about? The mean also has the units of whatever we're measuring. So for measuring volts, the mean has units of volts. And the mean, again, the reason I have the ballerina dancer there is that the mean is the point of balance. In other words, this ballerina who is balancing on her toes, that's the point of balance for her, right? And that's the same thing for the mean. The mean is where you have a point of balance. So this is the expected value of g of x as we have defined before. And this is kind of interesting because usually we use g of x is equal to x. Whoops. If I have g of x is equal to x, we have the integral of x times f sub x of x, right? And this is sometimes just denoted as the expected value of x. And sometimes it's just denoted as an x bar, an x with a line over it. In fact, often the expected value of g of x is just denoted as g of x with a line over it. So a line over it means the expected value of that. So this notation is the same as this notation over here. They're expressing the same results in different ways. Now let's take, I think, kind of an interesting case. Let's take this. It turns out that if this is true, then the derivative f sub x of x is equal to the derivative of this, which is 1 over x squared for x greater than 1, and we will just assume that it's 0 for other values. Is that okay? So this is an innocently appearing probability density function. You will notice also that the f sub x, if we were to plot the f sub x, it starts at 1 at a value of 0, right? And asymptotically goes to 1 as x goes to infinity, right? So therefore, it meets the criteria for a cumulative distribution function. The f sub x, the density function, also looks pretty innocent. It's 1 over x squared, so it starts at x is equal to 1, so it's 0 for negative, and it goes like this. It kind of looks like a exponential, but it isn't an exponential since the tails decay as, well, in polynomial 1 over x. But here's the interesting thing. What is the mean for this random variable? The mean for this random variable is what? The integral from 1 to infinity of x times f sub x dx, which is equal to the integral from 1 to infinity of x times 1 over x squared dx, which is equal to the integral from 1 to infinity of dx over x, correct? And does anybody remember from calculus what this is equal to? It's equal to the log of x. Recall that the derivative of the log of x is equal to 1 over x. So this is equal to the log of x between 1 and infinity. Well, the log of infinity is equal to infinity. So this is weird. This is weird. It's weird because the mean of this distribution is infinite. In other words, there's no point where this thing can balance. And one of the requirements for this is that this function goes on forever. This goes out to infinity, if you will. Okay, it keeps on going to infinity. And you have to have something infinitely long. If you have anything which is a finite duration, it's going to have a center of mass. It's going to have a point where it balances. But this thing, if you could literally create it, which you can't, because it goes out to infinity, would have no point at any place it would balance. Its mean is infinite. This is just curious, and this occurs. This occurs in a kind of an interesting way. So sometimes you have an infinite mean. I point this out because these are fun, kind of extreme examples of what these moments are. There's other examples that have a infinite second moment. And one of them is the Cauchy. Now, if you remember, the Cauchy if it's centered, is equal to a constant divided by x squared, say plus 1 squared. Well, let's just say b squared. No, let's just say 1 squared. No, let's say b squared. Okay, so in other words, it kind of looks like a Gaussian. It still looks like a bell-shaped curve in some sense, right? And it also looks kind of innocent, but its tails are very, very fat. And well, let's see, what is the second moment? Well, let's do the first moment first of all. The first moment of the Cauchy, x sub bar, is equal to the integral of minus infinity to infinity of xc over x squared plus b squared. Now, if we were to plot the integrand here, you notice this is an odd function, isn't it? So it looks like the mean of the Cauchy is clearly the area under this curve, which looks to be 0, right? Because this negative portion would eat up the positive portion and we would just be left with 0, correct? But there is a problem, and this problem is very subtle. It turns out that this has an infinite area and this has a minus infinity area. So in saying that this cancels out this, we are subtracting infinity from infinity, which is a very dangerous thing to do. We can get more rigorous, but that's a problem. We'll talk about this later. So there's kind of an ambiguity there, but where there's no ambiguity is in the second moment. This is equal to this integral. Is that okay? That's equal to the second moment. But if we were to plot the second moment, this is what we're integrating. This is the integrand without the c. Okay, at the origin, there's no problem. At x is equal to 0, it's 0, right? But what does this become for x going really big? X is equal to infinity. Do you remember these sort of things from calculus well enough? Can anybody tell me what this goes to asymptotically?
Would it go to 1?
Yeah, it goes to 1, doesn't it? Because if X gets really big, it doesn't matter what B is. The denominator is going to swamp out the B. So it goes to 1. Correct? And also, this is an even function. So on the other side, it also goes to 1, doesn't it? This is our integrand. And we're integrating from minus infinity to infinity of this integrand. Clearly, that's going to be what? Infinite, right? It's clearly going to be infinite. So the Cauchy unambiguously has an infinite second moment, a curious first moment. We won't delve into the curiosity of the first moment, but the second moment clearly goes to infinity. So the Cauchy is a weird random variable. The other thing, which is kind of cool, is that this is a problem that I gave you. The Cauchys exist in real time. I'm sorry, in reality, in the following sense. Say you have a cannon here. This is called the loose cannon. Two ends in cannon, yes or one? Okay, I'll abbreviate it then. So you have a cannon here, and this cannon is going to be measured. I want to do this very easy. I want to do it from here, theta. And theta goes from minus pi over 2 to pi over 2. So we're going to choose a random angle for the cannon. Is that okay? The next thing we're going to do is we're going to define a new random variable here, which is where it hits the wall. And let's just assume that it's 1 unit away. So X is where it hits the wall. Now X what is the tangent of theta? Tangent of theta is equal to X, isn't it? Right? This is a length of X. This is a length, I'm sorry, this height is a length of 1. And this leg is equal to X, right? So the tangent of theta is equal to, or is the cotangent of theta? No, tangent of theta. Is it the tangent of theta? Help me out here. Oh, I think it is the tangent because I'm used to the theta coming this way. Okay, so it is this tangent of theta. It's equal to X. So X is equal to the tangent of theta. This is a homework problem which I gave you. If theta is uniform between minus pi over 2 and pi over 2, then what is the distribution of X? And you will show that the distribution of X where the cannonball hits the wall is equal to a Cauchy. So you can see, at least in problems like this, that you do have Cauchy random variables. It also turns out that if you take the ratio between two independent Gaussian random variables of zero mean, you get a Cauchy. So Cauchys pop up all over the place. So it isn't something which is just pedagogical, something that I made up as something weird that doesn't exist in reality. Yes, we do have cases where we are confronted with Cauchys, and Cauchys are dangerous. They're dangerous because they have this infinite second moment, for example. Okay, I want to check the time. What time is it, guys?
1:24.
1:24. Okay, got lots of time. Now, if you have a discrete random variable, and we deal with discrete random variables when it suits us, we have probability masses here. We have probability masses. This is a probability mass function. And the probability that x is equal to x sub n is equal to something. So if we have x and we have x sub 1, x sub 2, and down here we have x sub 3, we can think of these as probability masses, if you will. Now, if we treated this as a continuous random variable, these would be Dirac delta functions, correct? They would be Dirac delta functions. Most of the random variables are of the lattice type, which means all of the probability masses exist at the integers. This was, I believe, a term which was coined by Athanasius Populus. But all of the probabilities lie at integers. So this is a random variable, a discrete random variable of the lattice type. So all the k-sub-n's exist at these points. But you notice in general, a discrete random variable doesn't have to have that criterion. The value of the probability masses do not need to exist at integer values. So we have all of these probability masses, and examples of them that we have gone through. The expected value of g of x is the Poisson, the binomial, and the Bernoulli. By the way, if you do have these point masses and you compute the mean is still the point of balance. It's just like you had a string and you had a bunch of point masses on the string, not a string, but a beam, and you had a bunch of point masses on this massless beam. Where would that beam balance? That's the mean, or the expected value of x. Same thing. Now, here's one of the interesting things about the lattice random variable. This is the expected value of x sub n. If we have a coin flip, and a coin flip has a 50-50 chance of being a 0 or a 1, and they both have a probability of a half. I should probably make these probability masses instead of Dirac delta functions. Where is the mean? The mean is clearly going to be a half, right? I mean, it's just kind of intuitively obvious. That's going to be the point where there is a point of balance, correct? Let me put my fingernails on the hand here. Okay, that's going to be the mean. So the mean is equal to, the expected value is equal to a half. Now that's kind of obvious, but here's what's curious about this. You ready for what's curious about this? The expected value can be something which you can never get experimentally. You can never flip a coin and get a value of a half. It always has to be a 0 or a 1. So the expected value need not be a realization of the random variable. I find this very curious, because you would expect the expected value would be something that we could have as a realization of the random variable. You'll notice even for a continuous random variable, if we have a random variable which has a probability mass here and a probability mass here and a 0 elsewhere, the mean can still be here. So even for a continuous random variable, the outcome of the random variable experiment need not be realizable as the mean. The mean can be something which is impossible to generate. So that's a curious result. I think it is. Let me show you also. I like to point out this very interesting chance. Okay, interesting cases. And this is a discrete random variable referred to as the St. Petersburg. Okay, sometimes it's called the St. Petersburg paradox. So don't read any of this. Here's the case. You come up to me and I'm at a casino and I run this table. And here's what's going to happen. If you flip a coin, well, let me explain this. You flip a coin n times and you get n minus 1 tails and then a heads. I'm going to pay you 2 to the n dollars. So you flip a tails, and you get a heads. I'm going to give you $8, 2 to the third. If you go tails, 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 heads, that's 2 to the fourth. So that'd be $16 that I would pay you. If you got tails, heads, that would only be $4 that I would give you. So it's ever how many tails you get in a row plus 1, 2 raised to that power. Does that make sense? So if you got 9 tails and a heads, that would be 2 to the 10th, which would be, I think, $1,024 I would pay you. Does that make a sense? So that's the game that we're going to play here. Now, here is where I'm going to appeal to your intuition. How much would you pay me to play that game? Clearly, you'd pay me more than $1, because if you flipped a coin and got 0, then I would say I give you $1, because that's 2 to the 0. So I give you $1, right? So how much would you pay me to play that game? Anybody hazard? Would you pay me $5 to play the game? All you would have to do is get 3 tails in a row and a heads, and that would be 2 to the fourth, which would be what? 2 to the fourth would be $16. All you'd have to get is 2. If you got 1 tail and a head, you would get what? $4, 2 squared. So you at least pay me a couple of bucks, I think. Would you pay me $4? Would you pay me $10? How much would you pay me to play the game? Intuitively, Theo.
I'm guessing it's $4 or $5.
That kind of makes sense, doesn't it? That would be a fair amount to pay me. Anybody else want to make a stab at it?
I think it'd be somewhere between 1 and 2.
$1 and $2. Okay. Yeah, that intuitively makes sense. But here's the challenge. Okay. Man, I can't find my cursor. Where's my cursor? There it is. Say that you had 1 flip, 2 flips, 3 flips, 4 flips, 5 flips, etc. And what's the probability of this happening? The probability of this happening is what? 1/2, 1/4, 1/8, correct? 1/16, 1/32. Is that right? That's the probability of this occurring. What is the dollar payoff? The dollar payoff is going to be 2, 4, 8, 16, 32. That's going to be the dollar payoff. So this is the random variable that we're talking about. So what is the expected value of your winnings? The expected value of your winnings are going to be the summation from k is equal to 1 to infinity of your winnings, which is going to be 2 to the k, times the probability of you winning, which is 1/2 to the k. So that's a summation of k is equal to 1 to infinity of 1, which is what?
infinity.
which is what is promised right down here, right? So this is no trick. This is the expected value. The expected value of your winnings is infinite. That's pretty incredible. This says that if I ask you $1,000 to play my game, you should say, no problem. My expected value of winnings is infinite. I'll pay you $1,000. Heck, if I ask you $1 million to play the game, you should go, yeah, no problem. I'll play the game because my expected value of winnings is infinite. Now, if you're really puzzled and think this is a really weird thing to do, if you think this is really a weird thing to do, you're exactly right. You know what, guys? I think that I did not start the recording here.
It says it's recording.
Is it recording?
Yeah, it says it is.
Okay, well, that's good. That's good. That happens when you get older. You forget things like that. So here's a question. My expected value of winnings is infinite. Now I want you to think, and I want you to tell me what's wrong in my reasoning and why should not I pay $1,000 to play this game?
That's because that will be the mean, the expected value. But in order to converge there, your average is not that big, the average. You have to repeat many times to get to approach infinity.
Yeah, you're
converge.
right. You're right. Your expected value is infinite. That's the expected value of your winnings. However, in order to realize this, you're going to have to play the game thousands of times to realize this. Because maybe 1 out of 1,000,000, you'll win $2 to the million or something like that. Okay. Or you'll win 2 to the, I don't know, you'll get 30. I guess 30 is $1 million roughly. So you'll
But
have
if
to,
you-
okay, go ahead.
But then wouldn't you be theoretically paid infinite dollars per hour?
Yes, you would. But one of the problems is you have to have an infinite amount of money to pay me to play the game. One of the things I learned, I was in this financial business for a while. One of the things I learned is in stock market trading that you have a risk reward ratio. This is just a general thought, and it might be applicable or not. You can get a risk reward ratio and make money as a function of time, which kind of looks like this. Whereas if you want to make more money, what happens to your risk? Your risk goes up, doesn't it? And so you might get a curve which kind of looks like this, right? Correct? But one of the things I found out, and this is really cool, is that if you get too much volatility, you might go down here and you might hit 0. And if you hit 0, you can't play the game anymore. Right? If you hit 0, it totally wipes you out. So I forget what the name of this is, but that's the problem. Is as the reward goes up, your risk or your volatility increases quite substantially, and you get to the point where you could be wiped out. So this is the same thing with the St. Petersburg problem. You would have to spend a lot of money. It doesn't matter how much I would charge you to play the game. You would have to pay a lot of money to realize these exorbitant returns. So it is the expected value. The expected value is infinite in the St. Petersburg paradox, but it is really, it's really weird, isn't it? It's a really weird problem, but it also exposes some of the challenges if you play a game just 1 or 2 times, what the mean can mean. the mean assumes that if you take an infinite number of realizations or an infinite number of ways to play the game, then and you average those up, you are going to hit the mean. But in the meantime, you're not going to hit the mean, and you could get this volatility problem. Okay. So that is fascinating stuff. This is something that a story I shared in multidimensional signal processing, but I once met the man, Adolf Lohmann, who was invented the computer-generated hologram. My career used to be focused very largely in optics, and I was really into things such as computer-generated holograms. Lohmann was the first to realize that if you were going to make a hologram, you could either go in the laboratory with lasers and things and make the hologram, or since you know all the math of light propagation, you could actually compute what the hologram could look like, print it out on a computer screen or whatever, and take a, make a transparency of it, and boom, there you had your hologram. And everybody thought at the time that holograms and optical computing were going to be the wave of the future. But unfortunately, computer-generated holograms and holograms in general really haven't made it, really haven't done very much. And I think that the place where you see computer-generated holograms today the most are in credit cards in order to avoid counterfeiting. So anyway, I was at Mackinac Island. I still remember it. It was at a retreat, and I was with the great man. And I'm sure that you know a lot of the luminaries today that if you got in their presence, you would just kind of melt because, oh my gosh, this is a guy I've studied about. I've studied his work, and I've read his papers, and he's so famous. And so I did that with Lohmann, and I sat down with him, and as a typical fan, I asked him kind of a silly question. I said, Dr. Lohmann, I says, you've not only done this, but you did a lot of other things. And he did do a lot of other things. And I says, you've done a lot of other things. Where do you get your inspiration? Where does this creativity come from? Can you give me, as a young professor, I was a young untenured professor at the time, can you give me some insight? And he smiled, and he was German, very thick German accent, which I won't try to duplicate. But he says, yes, anytime, here's my advice to you, anytime that you don't know what to do in the derivation or the pursuit of an idea, take a Fourier transform. And his advice to me, I think, was partly in jest, but it was true. His computer-generated hologram had to do with Fourier transforms. So anytime that you are confronted with a situation where you can't get to the next step in the formulation of a project, simply take a Fourier transform. So that was the advice that I got from Adolf Lohmann. I say this because that's the next topic. If you don't know what to take, if you don't know what to do with a probability density function, you take a Fourier transform. And that is referred to as the characteristic function. And this is an example of a characteristic function. It is the expected value of e to the j omega x. Now, the expected value of e to the j omega x is written as the integral. This is your g of x, if you will. And this is your g of x, if you will. So that's the expected value for a specific value of g of x. And you'll notice that the form of this is a Fourier transform. And yes, we take Fourier transforms of probability density functions. There's a number of properties, one of which is that the value of the characteristic function now is a function of omega, whereas before we're dealing with a probability density function of x. So just like in temporal Fourier transforms, we transform from time into frequency. Here we transform from x into omega. Now, all of the knowledge that you have about Fourier transforms is applicable here, but you have to let go of the idea that it's time and frequency. It's just mapping the probability density function into another domain, which we know as the Fourier domain. we know a couple of things, that that the characteristic function at the origin is equal to 1, because if I look at this thing and evaluate it at omega is equal to 0, this turns out to be 1, doesn't it? And so we're just left with the integral of the density function, which we know has an area of 1. It also turns out that the characteristic function, the magnitude of it, is always less than or equal to 1. So therefore, anytime you plot a characteristic function, you know that it has a value of 1 at the origin, and that every place else it's less than 1. Now, it could turn out that you do have a periodicity. And we'll find out that in the case of discrete random variables that you indeed do have a periodicity, and this 1 might repeat itself, but everything is less than or equal to 1. Typically, or always, for a continuous random variable, it never repeats itself. And you just get an equation which looks like this. One of the beautiful things about the characteristic functions, if you differentiate it, and this comes from the derivative theorem of Fourier analysis that we all know about. If you differentiate the characteristic function n times, then you get the nth moment. This is the expected value of n. And we can show this because phi of omega is equal to this. And we know if we differentiate this thing n times with respect to omega, well, the only thing that's a function of omega here is this e to the j omega x. So if we differentiate this n times with respect to omega, we get jx. I'm sorry, I made that a capital. I didn't mean make that a capital. We're differentiating with respect to omega, so we get jx raised to the nth power, right? That's what we get when we differentiate a. Does that make sense? Maybe I should. Maybe I should do this another way. Let me try it again with black and white. This is equal to e to the j omega x times f sub x of x dx. And if we differentiate it n times, we're going to get a jx raised to the nth power times e to the j omega x. We all know the rule for differentiating an exponential, I'm sure. And then if we evaluate this thing, if we evaluate this thing at omega is equal to 0, right? Then what we're going to get, if we evaluate it at n is equal to 0, the Fourier kernel goes away. And we're just left with the integral from minus infinity to infinity of jx to the n times f sub x of x. And you'll notice, except for the j here, this is the nth moment. It looks like this should be a plus j, by the way, according to my derivation here. So this is equal to, we bring the j sub n to the outside, and what's left on the integration is nothing more than the expected value of x sub n. Oh, no, it should be a minus. Sorry, I was right. I should never doubt myself. So the expected value of x to the n, if you take this j sub n to the other side, it becomes a minus j to the n. So this was correct. This was correct. So we can see here that one of the nice things about the characteristic function is that if you differentiate it and evaluate it at the origin, you do get indeed the expected value of the nth moment, which is really nice. And here's the properties. This, by the way, should be at the bottom. This shouldn't be here. This should be to the nth power. These are the properties that we have and that we've just shown. So I think now we're going to stop there since we've gone over a little bit, and we will talk about next time some of the characteristics of the characteristic function. Any questions at all? Okay, so for the next time, let's look over the homework that I've assigned you, and I'll answer any questions that you have. And until then, take care, be a good cheer. Bye-bye.
Everyone.